So in this video, I would like to introduce couple of more definitions and notations for the topic of limit, and it's actually quite similar to what we have been talking about, but we really have to try to make it more precise. You see, now I'm introducing some notations. The first one is called left-hand limit. Left-hand limit, please look at the notation here. I'm talking about x approaching a, but you see my notation, there's a superscript, which is a minus sign on top of a. And if you see something like this, you can think of it as a number line for the x-axis, and the point A is here. Minus basically means you are approaching x from the left direction, which means when you approach the point A, you have to choose values less than A. So as a very simple example, for example, if you look at this, you see, if you think of it as a problem of approximation, basically it means you're choosing values less than 1 for x, and it is gradually moving closer and closer to 1. For example, you can choose 0.9, and the next point is 0.99, the next point is 0.999, you see? So, and you can do the approximation here. So for example, it's 10.9, the next point is gonna be 10.99, the next point is 10.999. So there's nothing really different from what we did when I introduced the notation limit in the first video, and we did it by approximation. You see, when you make a good guess about how these values is approaching, it is actually approaching 11, right? So it looks like the answer is 11 in this case. So basically, it's really conceptually the same as the original meaning of limit, but you are restricting yourself to only considering values of x less than a when you do the approximation. And for the right-hand limit, it takes a very similar meaning. It takes a very similar meaning, but however, now you are approaching the point A from the right-hand side. It means that, for example, if you consider this same limit problem for the problem in the purple color I'm looking at, if you do it by approximation, you have to think of it as all the values of x are bigger than 1, and you are choosing them such that the value is approaching 1 gradually. So you can choose 1.1, 1.01, 1.001. And now you do this calculation, you get 11.1, the next one you get 11.01, the next one 11.001. You see, this trend of values give you an understanding that it looks like it is approaching 11, right? So it means the answer is 11 for this limit. And anyway, I certainly introduced this notation because I'd like to let you know that we want to fit this into the larger picture when we consider the topic of limit in general. The fact is like this, the fact. And actually, this fact makes sense. So basically, the fact is like this. This limit for x goes to a for the function f of x, without restricting the direction, like whether x is approaching a from the left or right, without any restriction. It means x can approach a from two different directions. Such a limit only exists if and only if the left-hand limit is the same as the right-hand limit. So and now let's look at an example where the limit when x goes to a may not exist, when the left-hand limit and the right-hand limit don't coincide. So let's look at this example quickly. So I can look at this example now. Let's say look at f of x such that this function equals x squared plus 1 for x less than 2, and for x at least the same as 2. It's gonna be let's say x plus 2, doesn't matter, so I just randomly put it like this. I hope you understand this function well. It means the function takes two different forms depending on the value of x, so when x is less than 2, for example, if you choose x equals 1.5, the expression of f of x is gonna be x squared plus 1. And similarly, for example, if you choose x equals 10, which is of course bigger than 2, then the expression of f becomes x plus 2. So now I can ask you, what is the limit x is approaching 2? And now, theoretically, this value you can only get it by taking approximation from left hand and the right hand uh, separately, for the left hand limit and the right hand limit separately. For example, you can try to find this first. For the left hand limit, you have to choose values of x less than 2, less than 2. And please look at this. When x is all less than 2 and approaching 2, it means the value of x stays here because all the values are now less than 2, less than 2. It means that for this limit problem, the function of x, f of x takes the form x squared plus 1. And as we have noticed before in the previous video, as a shortcut to the limit problem, for the simple function like polynomial, we can actually replace x by 2 directly. And the answer is 5 for this left-hand limit. And for the right-hand limit, because all the values now are bigger than 2, we can actually look at the second line of expression, which means the f of x is now the same as x plus 2. And we can actually, because of the fact that x plus 2 is again a polynomial, a simple function, simple enough that we can actually apply the shortcut rule. So I can just replace x by 2 inside to get 4. Now, please take a quick look. Please take a quick look. You see, these two values are not the same. Clearly not the same. It means, let's come back to our problem here. This limit does not exist, right? Because of this fact, they are not the same. Not the same. So I'm saying that the left hand limit is not the same as the right hand limit. So then the limit of f is not the same. I mean, it just doesn't exist. So that's basically the end of this video.